Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Houston, we don't have a problem. Hey, today what we're going to do is we're going to talk about this concept called Ohm's Law. And it talks about another concept called resistance. Resistance has to do with something that impedes charge flow. But I think to truly understand it, we're going to turn back to Tie-Dye Guy because he's got some cool stuff with clay, etc. So I want you to pay attention to Tie-Dye Guy as he really explains things really well.
Here's something we want to think about today. What is it about the 100-watt bulb and the 60-watt bulb that makes them behave differently when we hook them up to the same voltage? The electric outlet is 120 volts. When I hook this bulb up to it, it puts out 60 watts. This bulb puts out 100 watts. What is different about the bulbs? Now the bulbs are wires, and there's something different about the wires inside the bulb. That's a point we're going to talk about today, but we're going to do it not by working with light bulbs, but by working with Play-Doh. And I've got a chunk of Play-Doh right here, and it's hooked up to a power supply. I have a positive voltage here, I have a negative voltage here, and so current will flow through this chunk of Play-Doh. And I have a meter that I can use to tell how much current we have. And it looks like, let's see, I'm going to set this so we're getting about, let's get about 100 milliamps. Okay? That's a unit of current. So we're getting about 100 milliamps right here through this circuit. So I have 13 volts here, I have 0 volts here, and 100 milliamps of current goes through this chunk of Play-Doh. Okay? Now think about physically what's happening. Positive charges come out of the power supply, they come into here, they travel through the chunk of Play-Doh. As they do that, they lose energy and they end up at 0 volts at this end of the Play-Doh. Now, let's think about this. Let's think about this process. What would happen to the current inside here if I increased the voltage? What would you expect to happen to the current if I increased the voltage? We'll give you some choices. Well, if I increase the voltage, there's a bigger potential difference between these two ends. There's a bigger electric field inside the Play-Doh. The charges will move more quickly. Net result, the current should increase. And in fact, if I take this voltage and double it, what happens is this. The current goes up from 100 milliamps to 200 milliamps. Double the voltage, I double the current. That's not a huge surprise. So one thing that determines the current inside the Play-Doh is the voltage that's applied. Bigger voltage, bigger current. But there's another piece to the puzzle. And the other piece of the puzzle is the properties of the Play-Doh. Now we're going to bring this down to 100 milliamps again. So we're back where we started. Then I'm going to take this Play-Doh and I'm going to roll it out so that I have a thinner piece. I'll roll this out so I have a thinner piece. Longer, thinner. When that's true, and I put it on here, when I connect it back up again, how would you expect that to change the currents? Increasing the length, decreasing the cross-section area. How would that change the currents? We'll give you some choices. Well, it's not a huge surprise. Let's think about this. I have a bigger distance between these two terminals, so when I put this down here, delta V divided by delta D, the electric field is going to be smaller, and so I'll have less force on the charges, but also, because I have a narrower piece of Play-Doh, I won't have as many charges to be in motion, and so I expect, when I hook these things up, I will see a smaller current, and in fact, I do. And if I continue this process, I'll continue to decrease the current. Say, but it's not a huge surprise. That's how you might expect it to work. Now there's a property of the Play-Doh that we define as the resistance. And there's a definition of resistance given in the book. And it's an operational definition. The resistance is equal to the ratio of the voltage divided by the current. So the voltage from the power supply divided by the measured current gives us the resistance of this conductor. And if I have a higher resistance, that means I get less current for a given voltage. Resistance goes up, current goes down. But the resistance is a property of the material as well as the dimensions of the material. And if I take the material and make it longer and skinnier, the current will decrease. And we have some diagrams in the book that explain how you're going to expect resistance to change with the properties of a wire or other conductor. And we'll look at a bunch of different problems where we look at the resistance of different types of conductors. And it's a property of the material as well as the dimensions. Now let's take a look at what's inside a light bulb. And over here, I have a light bulb that's been deconstructed. So this is a light bulb just like this one, except what we did is we took it and broke the globe. Took this light bulb, broke the globe, and you can see what's inside is a wire. And when I pass a current through the wire gets warm. Now it turns out this wire is connected, we would say, in series with this light bulb. So any current that goes through this wire also goes through the light bulb. So we can use this light bulb as a measure of how much current there is in the circuit. Bright light bulb, the current is big. Dim light bulb, the current is small. So if I take this and plug it in, the light bulb lights, there's a current inside the circuit. Now I want you to do this. I want you to watch this light bulb. This light bulb, when I blow on the filament's warm, and when I blow on it, it will cool. When I blow on it, it will cool. Watch the brightness of this bulb as I do that. And you can see, when I blow on the filament, the brightness increases. When I blow on the filament cools. The brightness of the bulb increases. So here's a question for you. When I blow on the light bulb filament, and thus cooling it, how does it change the resistance of the filament? How does the resistance of the filament change as I cool it? We'll give you some choices. Let's think about this. This is one continuous circuit. When I blow on the filament, the light bulb got brighter. And so it says the current that is shared between this filament and the bulb increased. If current went up, that means the resistance went down. So it decreases the resistance when the temperature goes down. And we can see that. So now let's think about these light bulbs. 60-watt light bulb, 100-watt light bulb. How do I make different brightness light bulbs? This light bulb is brighter, it has more current than this light bulb. So here's a question for you. Which bulb has a higher resistance, the 60-watt bulb or the 100-watt light bulb? There's definitely more current in this bulb, it's brighter. More current. 60 watt, less current. So which bulb has a higher resistance, the 60-watt bulb or the 100-watt bulb? We'll give you some choices. Well, in fact, if this bulb's brighter, it has more current in it. More current means less resistance. And so this light bulb has less resistance than this one. There are wires inside both these bulbs, and it turns out this bulb is slightly longer. And because it's longer, it has more resistance than this one. More resistance, less current, less brightness. And you would change the brightness of the bulb by changing the length of the filament, ultimately.